The circuit that we analyzed so far was this. The gate is incrementally grounded, and we have a load, and the input is connected to a source resistance Rs. And this equivalently can be also thought of as a current source in parallel with resistance. The current source value here will be Vs by Rs, but you can think of it as an independent current source. Let me change the notation a little bit. I will make this Vi instead of Vs. Okay. And the output is taken here. What is V0 by Vi? What is the expression we obtained for V0 by Vi? That's approximate. Let's get a more exact version. So the full expression was something like this. There are a couple of approximations to this. One where you get RL by Rs plus 1 over Gm, or you can also further approximate it to simply RL by Rs. Okay. This is the gain at DC. What happens at AC? Where are the parasitic capacitances? Where are the parasitic capacitances in the circuit? Gate source and source to drain. There is no direct capacitance from source to drain in the model of the MOSFET. In very short channel MOSFET, you do get some capacitance between source and drain, but it's typically very small, and most of the time we completely ignore it. There is a channel capacitance between gate and drain, which in saturation region is mostly due to overlap. What else? Drain bulk and source bulk. These are junction capacitances from the source and drain junction to bulk, which also is incrementally grounded. Now, CGS and CSB are in parallel with each other, and CGD and CDB are in parallel with each other. Okay. So basically, there are capacitances between the source node and ground, and between the drain node and ground. Okay. So what I will do is I will remove these and replace it with a single capacitance from each node. Okay. I will call this CL and I will call this CI. CI is the capacitance from the input node to ground. CL is the capacitance from the output node to ground. CL consists of CDB and CGD and anything else you connect. For instance, it could be the input capacitance of the following stage. It could be an explicit capacitive load. Similarly, CI is CGS plus CSB plus any other parasitic capacitance you may have because of interconnections. What will be the gain in presence of this? Again, we can go back, write the node equations, analyze the circuit. But we already know the DC gain and we know the capacitance values. Okay? Can we say what the AC transfer function will be? Before going to that, what is the order of the circuit? Second order. Why? So, looks like there are two capacitors and the voltages across them are independent of each other. Okay. So, we likely expect a second order transfer function. But what is the transfer function? Is there an easy way of obtaining the transfer function? Huh? Okay. So, one suggestion is that we ignore GDS in the analysis. So, not sure what all that is about. Anyway, so if we ignore GDS, we have this. Okay, so this is the gate, drain and source, CL and CI. Is this easier to analyze? His suggestion was that we analyze this circuit and it's easier. Why is it easier? So there is no coupling between the two. What is the impedance looking up like this? 1 by Gm. So what is the voltage at this point? The input impedance looking up is exactly 1 by Gm if you don't have GDS. Okay. So what is the voltage at the source node under this condition? Okay. What's the DC gain from, again I mistakenly wrote Vs, let me correct it to Vi. Yeah? Yeah, let's come to that. That's actually more general. Okay. Yeah, we can do that. First, let's look at what the result from this is and move on to that one. Okay. What is the DC gain from this point, from here to here? Huh? Yeah. So it's 1 by Gm by 1 by Gm plus Rs, which basically is 1 by 1 plus Gm Rs. Okay. So the source node voltage is small. That's the general idea. You always get it to be like that. Okay. And what is the order of the transfer function? From Vi to the source node. First order. Where is the pole? So the pole is at Gs plus Gm by Ci, right? So the total conductance of this node, which is Gs plus Gm divided by the capacitance you see, Ci. Is this part clear? Essentially, I represent whatever is up here by a conductance Gm, okay. Then I simply get this to be the pole. Is this okay? Fine. So that's the voltage at the source node. So what is the voltage at the drain node now? What is the voltage at the drain node in terms of the voltage at the source node? So if the source node is at Vs, this current source is pointing upwards with a scaling factor of Gm. And what is the voltage at the drain? Here. So this current divided by the parallel admittance. Okay. So the voltage here is GMVS divided by GL plus SCL. Okay. Which also can be written as Vs times GMRL by 1 plus SCL by GL. So there is another pole here and the frequency of the pole is GL by CL. The pole is at minus GL by CL. And if I combine the two, the transfer function turns out to be GMRL by 1 plus GMRS. This is the DC gain. As you can see, when GM becomes very large, GMRS becomes much more than 1, you will have RL by RS. Okay? So you should get that. And there are two real poles. Okay. We get a DC gain of nearly RL by RS as we expect, and we get two real poles. One of the poles is at CI by GM plus GS and the other one is at CL by GL. Okay. This is under the approximation that GDS is negligible. But once you neglect GDS, the rest of the analysis is exact. This is what you get even if you write node equations and solve it step by step. Okay. So you get two separate first order systems in cascade. That's what this is saying. Which is the high frequency pole? Which is the low frequency pole? The pole associated with the source node tends to be the high frequency pole because it has a conductance of Gm, which is much more than anything else. The parasitic capacitances, without any further information, we can assume them to be of the same order. Okay. And that's reasonable also. Here you have CGS plus CSB. Here we have CGD plus CDB. CDB will be the same as CSB, more or less. CGD will be slightly smaller, but we have to keep in mind that the output will be connected to the following stage. So it's likely to have a greater load. This is the high frequency pole and this is the low frequency pole. What is the difference between this and the common source amplifier? What's an important difference that you see? The absence of a zero. Okay. And that turns out is a crucial difference because if you have some coupling directly between more than the zero, if you have a capacitive coupling between the input and output, you change something on the load side that influences the impedance on the source side. So it can give you problems when you have a number of amplifiers in cascade. Okay. You say, let's say you have amplifier 1, 2 and 3. Now you change something in amplifier 3, the gain of the first amplifier changes if you have a coupling across the second amplifier. Okay. Whereas a common gate amplifier will not have this coupling, so it provides a much greater isolation between what is before it and what is after it. Okay. So if you want good isolation between the input and output, a common gate amplifier is a better bet. Now let's say I didn't want to ignore GDS, I wanted to calculate the transfer function. Is there something I do? Is there something I can do based on what I already have? So that was the suggestion he gave earlier, that all that has happened is, this expression, the DC gain expression, consists of GL and GS. Okay. First of all, we can use the alternative representation. That is, I put the current source here. So this is II, which if driven from a voltage source is VI by RS or VI times GS, and there is a conductance of GS from this node to ground. The expression involves GS and GL, and the high frequency equivalent circuit, the only difference is that instead of GL you have the parallel combination GL plus SCL. Okay. Instead of GS I have the parallel combination GS plus SCI. Okay. So in the expression, wherever I see GS, I put GS plus SCI, and wherever I see GL, I put GL plus SCL. Okay. So I don't have to redo the whole analysis, I can get it from this expression. But the important thing is I have to do this source transformation first. Okay. I have V naught by Vi here. V naught by Vi was 1 by, let me write it exclusively in terms of conductances. Okay. Now if I wanted V naught by II instead, what do I have? The whole thing into RS, right? Whole thing into RS, which basically becomes so in this I do the substitution. Pardon? Yeah, you can. Like I said the other day, if you use the frequency dependent gain in the Miller effect, the expressions will be exactly right. Okay. Now, yeah, if you use it from the DC gain, first of all, it's not hard to do the DC analysis, right? So once you do the DC analysis, you don't have to do it anymore. So it will be true only for DC. Okay, if you calculate the high frequency pole based on that expression, it will be not correct. So you can do it, that's the bottom line. You can do it. The low frequency transfer function will be right if you use Miller effect on GDS, but it's not all that productive. First of all, the effect of GDS is very small in this circuit, so it's not all that beneficial to use the Miller effect on GDS, but you can certainly use it. Okay. So this is what we get. It's some second order expression. I won't bother to expand it, but as you can see, you will get some second order expression. And if you neglect GDS, what do you get? You should get back the original expression. This is V naught by II. Okay. If I neglect the value of GDS, I will get GL plus SCL here by GM, okay, which is exactly what I had before. So as expected, we do get the correct answer if you neglect GDS. So if you don't neglect it, you will get a slightly modified version of the transfer function. If you want, you can put typical values of GDS into it and calculate the poles. Okay. Yeah. So the DC gain gets modified slightly because of GDS, and the poles also will get modified slightly because of GDS. Okay. What will? See, yeah, we can, if you want, we can work that out. This is the expression for V0 by II. Okay. If you want V0 by Vi, you just divide it by Rs. That's all. So, I am not sure if it is worth expanding this to see. See, the only thing I will say is, what is the effect on the input impedance because of GDS? It increases. Yeah. So, the input pole goes to a lower frequency. Okay. So, that is basically what happens. And the output impedance was infinity. Right, output impedance excluding RL was infinity without GDS, and with GDS it is some finite quantity, which is GM, approximately GM by GDS times the source resistance. So that comes in parallel with RL, so the poles move a little closer together. So that, I mean, sort of intuitively makes sense. Let's go to the absolute extreme case where we sort it out with GDS equal to infinity. We get a first order system where essentially the two poles merge into each other. So the reason it's not usually calculated is GDS can be reasonably assumed to be much lower than GM most of the time, right? In any reasonable amplifier design, even in a short channel technology, GM by GDS is of the order of 10 at least, about 10 also. So yeah, but as the question was what happens with GDS, and the answer is if the looking in impedance here does increase if you have GDS, okay. If you don't have GDS, it's just 1 by GM. If you have GDS, we saw that depending on the value of RL, it can increase. Okay. So that pole will move slightly to lower frequencies. So the higher frequency pole will move to slightly lower frequencies. Okay. Now that's not an exact analysis because once you have CL here, okay, The looking in impedance also consists of some part because of CL, but roughly what I said holds true. So compared to the common source amplifier, the main difference is in the isolation. That is, there is no direct feed through between the input and output, and that's a great advantage of the common gate amplifier. Okay. Any questions on this? And in most cases, you can approximate the two poles to be the input impedance, which is roughly 1 over Gm divided by the input capacitance, and the output impedance or the load impedance, load conductance divided by the load capacitance. Okay. Now, of course, if you have an open circuit load, this doesn't apply. Then you will have to do something else. And the output pole or the pole on the load side tends to be the dominant pole because it's at lower frequencies. Any questions? Yeah, that's roughly what we did, right? The first time, especially when you neglect GDS, in this case it gives you the exact answer. So the time constant at each node is nothing but the product of the impedance you see, the resistance you see at this node times the capacitance you see at this node. And the reciprocal of that is the pole. Okay? So this is the time constant, right? Ci by Gm plus Gs, it is the time constant associated with the input node. CL by GL is the time constant associated with the output node. So that's what we are using. No, I mean, if you can identify separate time constants, okay, if I do something like this, then it's not really valid. Okay. So there are techniques when you have multiple capacitors and resistors to find out exactly, I mean, not exactly, approximately the effect of all of them combined into a single time constant. Okay. So there is something known as the method of open circuit time constants. Have you heard of this? It's a long time since I saw it, but let's say we have something of this sort. I think the way it goes is with this you can find the time constants or all the poles associated with stuff. So you disable the input, okay, and let's say you have a number of capacitors. In this case I will take 2. So you first take one capacitor. When you are dealing with a particular capacitor, you open circuit every other capacitor. Okay. So this is the circuit we have. Okay. And you look at the resistance that appears across the capacitor. What is it in this case? R1? R1 parallel R2? Why? This is open circuited on this side. Okay. It's just R1. That is the time constant when you open circuit C2 or when you keep only C1. And let's open circuit C1 and keep C2. Okay. What is the time constant associated with this? Huh? R1 plus R2 times C2. Okay. And I forget exactly, I think the theorem goes that the circuit can be represented approximately with a first order system whose time constant is the sum of all these time constants. Okay. Is this, if any of you remembers it and this is wrong, let me know. Huh? Yeah, that's what this is. Elmore delay model is the method of open circuit time constants. So, the circuit can be represented by a single time constant, which is the sum of individual time constants. Here the individual time constants are evaluated by open circuiting all capacitors except one, and by looking at the resistance across the capacitor and computing the time constants. Okay. So, we can actually, I am curious to see what the result will be. So, let us evaluate the transfer function of this. If we evaluate the transfer function of this, so an easy way to evaluate this ladder transfer function is to go backwards. Okay. This is V naught. What is this? Is there an easy way to find that out? It's a low pass filter from here to here, right? So this times 1 over SC2R2 is V naught. Okay. So anyway, let me go step by step. What is this current? V naught times SC2. What is the voltage drop here? It is V naught times SC2 times R2. Okay. So what is the voltage here at this point? V naught 1 plus SC2 R2. Okay. What is the current here? That whole thing times SC1. What is the voltage drop across this? Into times, this times R1. What is the input voltage now in terms of the output voltage? So voltage drop across R1, right? It's this voltage drop plus this voltage drop plus this, isn't it? Just going around the loop. So VI is no, this was wrong actually. Sorry. The analysis was not correct. What is the current through R1? It is the sum of these two currents, right? So one part was omitted. The current through C1, the current through C1 is this much. Okay. But the current through R1 is the current through C1 plus the current through C2. Isn't it? So that part I had omitted. So the voltage drop across this is this plus V0 times SC2 times R1. Is this clear? I have a certain current here and a certain current here. The sum of the two flows through R1. The current through C2 flows through R2. So the input voltage is this is across R1, this is across R2, and this is V0 itself. Okay. So all I did was to work backwards from the ladder, starting from the output. So the transfer function is this. The open circuit time constant we evaluated, what was that? What was the open circuit time constant we evaluated? So it was C1 R1 plus C2 times R1 plus R2. And if I write the transfer function using the method of open circuit time constants as a first order one, it will be okay. So it's like neglecting the higher order terms in the transfer function. Okay. So it is many cases a reasonable approximation to it, but clearly, I mean, this is a second order transfer function and this is a first order transfer function. The first order function cannot reproduce all the features of the second order function, but when you are calculating delays and so on, which is of interest when you do this Elmore's method, or especially when you do it for digital circuits, you are only interested in how much total delay there is. For that, it's quite useful. You guys have seen this in your digital course or what? Okay. Any other questions? When we initially had analyzed feedback systems, we had also seen that ideally we would want the loop gain to be an integrator, or in the time domain to be a ramp, and if we have an additional pole, we get a delay equal to the time constant associated with that pole, and if we have multiple poles, the delay for the ramp will be the sum of the delays. It is something like that, right? It is similar to that. We have multiple time constants, then if we have multiple poles, the total delay for the ramp will be sum of the reciprocal of the pole values. Okay. The poles are a property of the network. The question is, when you are calculating the poles, should you look at the signal path? The signal part doesn't come into picture. The poles are independent of where you apply the input and where you take the output. Okay. So you disable the inputs and you evaluate the poles. Now where you apply the input and where you take the output from will determine the zeros. Okay. So for instance, if you determine the poles using this method, let's say the method of open circuit time constants, what you then do is you evaluate the DC gain from your particular input to the particular output you are interested in, and then divide it by 1 plus S by P, where P is the effective pole that you calculate. Okay. So where you apply the input and where you take the output only change the zeros, not the poles. Okay. You are familiar with state space representation, which is used in controls and other things? What is the solution to this in the Laplace domain? Si minus A inverse times B something. This is the state is this, okay, and this you put into A, Y to this you put into the other one. So anyway, the thing is, you look at the denominator polynomial which comes from Si minus A inverse. It only depends on A, okay. It only depends on how the derivatives are related to the states, not on the input, where you take the input. And roughly speaking, this B represents where you apply the input and C represents where you take the output from, right? Isn't it? Y is some C times X. So that means like you combine the states in some way and take that as the output. And B times U is the U is the input, so B times U is added to the derivative. Okay. So B roughly represents where you apply the input. It's not dependent on that. It's only Si minus A inverse that gives you the denominator polynomial. Okay. And you know that basically the poles are nothing but the eigenvalues of A, right? And you can evaluate it. I think we have done it a few times. So if you R and KR, this is a classic example, right? So you can use it as a non-inverting amplifier of gain K plus 1, or you can use it as an inverting amplifier of gain K. So in this case the gain is minus K. The poles will be the same. You can evaluate it and see. And you can even put parasitics if you want. You can put a parasitic from here to ground. Okay. It will only change the zeros. Anything else? Any other questions on this analysis or anything else we have done so far? I didn't hear. Could you repeat that? Okay. So first of all, the DC gain does not have a negative sign. So there is not much motivation to put it around it, right? At least it's not a negative feedback system, right? It's more like positive feedback, except that any resistance you connect also influences the gain itself. Okay. Now how it influences the gain, that can be easily seen. If we have the expression, right? We have the expression for the gain here. Now any additional resistance you connect across GDS, or it could be in general any impedance also. Okay. I will call it uppercase GDS. You simply add it to GDS. Okay. How will it affect it? So first of all, we saw that looking in impedance, for instance, it was GM, 1 over GM when there was no GDS, and it was increasing. It was influenced by the load resistance when you have GDS. If you further increase GDS, the influence of the load impedance will increase. Okay. Essentially the input impedance will increase. Okay. That's the influence of GDS. Similarly, what will happen to the output impedance? What will happen to the output impedance? What is the expression for the output impedance? Please look it up and let me know. It will decrease because the predominant part of the output resistance was this RS getting multiplied by GM by GDS. If you increase GDS, the factor GM by GDS will reduce and the output impedance will reduce. So in general, it will make the amplifier a little worse, right? If you think of the common gate amplifier as a current buffer, you want zero input impedance and infinite output impedance. In reality, you get an input impedance roughly 1 over GM and an output impedance of something GM by GDS times RS. If you reduce the value of GDS, the input impedance will increase, the output impedance will decrease. So it will make it a worse current buffer. Okay, that's the main effect. You will not introduce an additional pole because if you look at the 3 voltages, just like in the common source amplifier, only 2 of them are independent. Okay. In the common source amplifier also you have this network of capacitors, CI, CL and a capacitance across the gate source, gate drain. So in this case it will be across drain source. What it will do is it will introduce a 0. Okay. So it will still be a 2-pole system, but it will introduce a 0. Where will the 0 be? In the right half plane or the left half plane? Why? So, in case of the common source amplifier, the current source controlled by this terminal was in the downward direction, and this was pushing current like this. Okay. Now, in case of the common gate amplifier, if you think of the source voltage as a controlling node, the current source is pushing up, and if you have a capacitance, that also pushes up a current. So, if you write the Kirchhoff's current law equation, you get Gm plus SCX instead of Gm minus SCX. So, that gives you a left half plane 0. Okay. So, that again, what does it do? The same thing that I described earlier will happen, but in a frequency dependent fashion. Okay. If you look in here, low frequencies, you will see approximately 1 by Gm. Because of the capacitance, it will increase at high frequencies. Okay, the input impedance will increase at high frequencies. What kind of an impedance is that? It's an inductor, right? If you have, it will look like 1 over Gm in series with an inductor. Okay. Similarly, the output impedance, it is Gm by this whole admittance times Rs. That is the total output impedance. Now, the admittance keeps on increasing, so the output impedance keeps on decreasing. So, the output impedance will appear capacitive. Okay. So, whatever we describe now, it will happen, but as frequency increases, it becomes a worse current buffer. Okay. You will not be able to do it. You will not be able to do it because the pole is also dependent on this capacitor. You can try out the expressions if you want, but you will not be able to find the value of this because you cannot independently adjust the pole on 0. If you, let's say this is the coupling capacitor Cx, if you connect it, that will also influence the pole, and you will see that it will not be able to cancel anything. Okay.
So what is the frequency in
the input impedance? No, I am only basing my intuition on this thing, right? If I plot it versus frequency, at low frequencies I will see 1 over Gm. Let me assume that RL is not very large or anything. And I also know that GDS influences the input resistance, input impedance. Sorry, GDS or in general the admittance here. So, if the admittance increases with frequency, I expect the output impedance also to increase a little bit with frequency. I think that's what happens. I'll work it out and see. So, let's say, normally this is a common gate amplifier and the gate should be biased with some fixed potential. Okay. So, let's say we do it with an ideal voltage source. This is the bias voltage. Now, we don't know that there is no such thing as an ideal voltage source. It has some resistance. Okay. What will be the effect on different aspects of the common gate amplifier we have discussed so far? Will everything remain the same? Now, we have evaluated the gain, input impedance and output impedance, and for an amplifier there isn't much else to evaluate. Okay. So, what will happen to any of these things? Well, have you seen this type of circuit before? To be precise, in the first assignment. Have you seen it or no? How many of you have seen it? Only one. I think I'll reduce the assignment 1 marks to everybody else. You haven't seen this at all? You go back and look at it and figure out what happens.